Welcome, folks. I decided to give a sequence of videos over Laplace transform. And the reason is that Laplace transform is very useful and very important for engineering students. But I decided to cover this sequence of videos to not only help you with your classes if you are studying Laplace transform, but if you have already studied Laplace transform, then you can look back into it and relate to Laplace transform. Hopefully this will give you a better understanding not only to the mathematics, but also how you can use it and why they do work. In this particular video, I will go over the introduction of Laplace transform. I will introduce it. I will show you some aspects from it. Hopefully some of the stuff I will present in this video will also be additive to you. So let's start. Basically, we can say that Laplace transform converts the time domain signal f of t into the complex frequency domain signal f of s. So here we are interested in the domain. The domain means the variable of the function. So the signal is a mathematical function that carries electric characteristics. Right, so any kind of signal is a mathematical function. Its domain is the time domain, f of t. We're gonna convert it to f of s, where s is the domain here. The domain is called complex frequency because s is a complex value. So we usually say that s will equal to sigma plus j omega. For example, we can say that s will equal to 3 plus j5. Sigma here will be the real value, 3, and omega will be the imaginary value, 5. So the frequency s, the domain, is complex value. So we call it complex frequency. So it's a conversion, is a mapping. Basically, to convert the signal from one signal to another one is called mapping. Here we are converting the domain. So you start with a signal f of t. It's in the time domain. You want to convert it, you want to map it to a signal called capital F of s. In a new domain, we call it the complex frequency domain. This transformation, this conversion, we're going to call it Laplace transform. We're going to convert it through the Laplace transform. So the Laplace transform is nothing but integral. F of t is double-sided signal. Then the transformation f of s will go from minus infinity to infinity of f of t times e to the minus st dt. So the word double-sided means that f of t is defined for all value of t, the negative values of t and the positive values of t. Then this transform or mapping is called an integral mapping. This mapping is basically something we call projection. You're projecting f of t, you're multiplying f of t into e to the minus st, and then you integrate for all values of time. This is called projection. I will make another video to talk about the meaning of projecting f of t into e to the minus st. Is if you have two functions, you wanted to say how they are related, you multiply them together and then you integrate over the time. And that would tell you how related those two functions are. But here, I'm projecting f of t over e to the minus st for any value of s over all t. That's a projection of f of t into e to the minus st over all values of t. That's the meaning of it. Now, for all practical purposes, many signals gonna be 0 for t less than 0. So, and this is useful. So, for example, you're gonna turn on the switch, right, for a circuit. If you turn on the switch for a circuit, we know that before turning on the switch was 0. So if the signal is 0 for all values of t less than 0, we call that single-sided or causal signal. So if it is a causal signal, the transformation itself is going to be single-sided. So we're going to say that f of s is going to be the integral of f of t times e to the minus st dt. from 0 minus to infinity, right? Because we know that f of t can be 0 for any values of t less than 0. So this here is a causal signal. F of t is a causal signal. This is a very practical transformation. So in summary, to convert f of t to f of s, if it's non-causal signal, if it's double-sided, you use the double integral. If it is causal signal, you use this one, right? Basically, you multiply the signal times e to the minus st dt, and you integrate from 0 to infinity. Here we added the 0 minus to be able to integrate the delta t, which is the impulse function, with the single-sided definition. It is definitely going to work here, but for the single-sided definition, the delta t, the impulse function, is included here. We can also get the inverse of Laplace. So if you start with f of s, you can go back to f of t, and you can do that with the inverse equation. So the inverse of Laplace uses something we call the contour integral, or the Cauchy's contour integral, because f of s is a complex function. So, and you wanted to take it back again to the time domain. So the way you want to do that is you're going to use this integral. It's basically evaluated using the residue. It's called the closed contour, or the Cauchy contour integral equation, where you're going to say that f of t will be 1 over 2 pi I times the integral of a closed contour from sigma minus j omega to sigma plus j omega times f of s times e to the st dt. Basically, what you wanted to do is you wanted to multiply f of s times e to the est, and you wanted to integrate for all values of s. For all values of s. So here we're doing the opposite projection. We are projecting all f of s for all values of s into e to the st. That's the inverse projection, right? And you want to do it for all values of s, and that will give you f of t, because t becomes the only variable that is unknown. In later videos, we will prove also the inverse equation does work. If this is your f of s, then this is going to be the inverse of it. There is a proof for that. To understand how to calculate this, you need to understand how to calculate complex functions. And you can take derivatives and do integrals on this complex function. So it looks puzzling for students when they say that I can't calculate this, and I have to rely on partial fraction expansion to get the inverse. The reason is they don't know how to calculate this integral when f of s is a complex function, or when s is a complex variable. S is sigma plus j omega, is a complex variable. So that's a puzzling for some students. So we will have a video to talk about that later on also, that will help you have a deeper understanding to the mathematics and why Laplace Transform is so interesting and so beautiful tool, and it is useful in engineering, as we most of us know or will know as we continue in our studies. So let's show you example and how to obtain f of s for a given function. So here we're going to look at f of t will equal to a times e to the minus at u of t. So this here is a causal signal, because the u of t is the step function. It says that it is 0 for all t less than 0. It is 1 for all t greater than or equal to 0. So if you multiply that by this, then what you will end up with is you're going to have that for t greater than 0, but it is 0 for t less than 0. So it becomes a causal signal. So it's a causal signal here. And now we're going to show you that it's a transform. If you compute this integral, it's going to tell you that the transform is going to be a over s plus a. But we have to also say that this integral will converge. We call it region of convergence, ROC. This integral will converge when sigma, the real part of s, sigma is the real part of s, is greater than minus a, and minus a is this exponential function over here. So here I'm carrying the math, which is something is beautiful, carrying the math. Let's look at the math and let's see what we have. So we're going to say that f of s will equal to the integral from 0 minus to infinity of a times e to the minus at times e to the minus st dt. Basically, I'm using this one because f of t is a causal signal. It is 0 for all t less than 0. So I'm going to pull the a out here, right? And then what I'm going to do is when you pull the a out, you have exponential function times exponential function here. So I can add the exponents. The exponents are negative. So I'm going to say that I'm going to integrate times e. I will pull the minus sign out, and I will have s plus a. I basically added the exponent terms times t dt. So now I'm going to take the antiderivative. So the antiderivative of e to the s plus at gonna be, I have the a here, right? And then I'm gonna divide by the minus, so I have the minus in front here, and then I will have e to the minus s at dt. I will divide by the exponent, which is s plus a. It should be the minus here, I just took it to the top, right? So this is the antiderivative. I'm integrating from 0 to infinity. So I'm gonna basically calculate that. So I'm gonna pull the minus a over s plus a out, and then I will evaluate this term here when t equals infinity and minus when t equals 0. So that's what I have here is e times e to the s a times minus infinity, because the minus sign here, when you multiply it by infinity, it becomes minus infinity, and then minus e to the s plus a times minus 0, because t here going to be evaluated as 0, but you have minus, so you get minus 0. Minus 0 is the same as 0. 0 times any value is 0. Then e to the 0 is basically 1. So this term going to be 1. The challenge here is how we are going to evaluate this. How we are going to evaluate this. This is the challenge. And now what we're going to do is I'm going to basically flip the order here to make the minus sign positive. So if you multiply the minus here, you get minus here plus here. So if I flip the order here, I get rid of the minus sign. And then I will show you how to calculate e to the s plus a to the minus infinity. So now what I'm going to do is I'm going to flip the orders here basically by multiplying the minus sign inside. So it will be plus 1 and minus that. And then I'm going to substitute for s with the value sigma plus j omega. I will bring this here and I will flip the order. So when you do that, now the minus sign is gone. So I will have a over s plus a. I have the 1 first minus e2, replacing s with sigma plus j omega, that's what I have, plus a times e to the minus infinity. Now what I'm going to do is I'm going to break this exponent. So I'm going to group the real values, which are the sigma plus a, multiplies them by minus infinity. And remember that if you add exponents, it's the same as multiplying the two exponential functions together. So I'm going to play with this here. Basically what I will have is the a over s plus, the capital A over s plus small a over here. So this term is the same. The 1 is the same. What I will have here is e to the sigma plus a times minus infinity multiplied by e to the j omega times minus infinity, basically by breaking the addition of the exponents within the exponential functions, they became multiplication. Now we're going to focus on this one. This one here is a periodic function, right? E to the j omega any value. The magnitude of that always 1. It just changes the phase, right? So we are interested in this term. So this is what we are interested in. So as long as sigma plus a is bigger than 0, so we will have e to the positive value times negative infinity. This will give us e to the negative infinity. So if this is the case, the entire term here gonna go to 0 because e to the negative infinity is 0. Multiplied by anything gonna be 0. So this function will be 0 as long as sigma plus a is greater than 0. So if this is 0, then the function is nothing but a over s plus a. That's what I have here, times 1. But this is true as long as for all sigma is greater than negative a, which is basically what we said earlier, that this exponential function, if it's causal, if it's 0 for all t less than 0, that is its transform, and it will converge. The integral will be valid as long as sigma is greater than negative a, right? So what we did here is we started with f of t, and we were able to convert it to f of s, where f of s is called the Laplace transform of f of t. What's important here is f of t was a real function, its value is real, and its domain is t, is the time domain, where t is also a real value. So here we say that at t equal 5, for example, f at 5 will equal to some real value. So you start with a real function, but f of s is complex function. You end up with a complex function. So its domain s, the complex frequency, is complex value. So for example, you're going to say that s will equal to 2 plus 3j. J here is the square root of negative 1. It's the same as I in mathematics. So for example, for a given arbitrary function, we can say that f of 2 plus 3j, right? This is the Laplace transform at given frequency, will be a complex value. It might be something like that, 2 plus 3j. So a complex value means that it's going to have a magnitude and a phase. So let's show you a better example to have some understanding of what's going on here. So let's say that you have a function f of t that will equal to 5 times e to the negative 3t u of t. If you plot this function, this is the function, it's exponentially decaying function. It is 0 for all t less than 0. For t greater than or equal to 0, going to be exponentially decaying function like that, right? Then it's a transform, f of s will be 5 over s plus 3, because 5 is the amplitude and the exponential decaying coefficient, which is 1 over tau, is negative 3. So the transformation will be 5 over s plus 3. Now, f of s is a complex function, and the domain, all values of possible s, is called the s-plane, right? All possible values of s is called the domain. So here we have the real axis, we call it the sigma axis, and the imaginary axis is called the j omega axis. That's to represent s. So we call it the s-plane, which is the s domain. So it basically represents all possible values of s, the possible domain. This analogy is very similar to the time axis. The time axis here represents all possible values of t and f of t. The s-plane represents all possible value of s into f of s. It's the domain of f of s. Now, if we're going to plot f of s is a complex function. So the way you want to plot it, you're going to get the magnitude of f of s and the phase of f of s as a function of s. So if this is your function of s, this is the real axis, this is the imaginary axis, this is the magnitude of f of s, and this is the phase of f of s. So when you plot a function, a complex function, the domain is a plane, then you can't plot f of s because you can't visualize it. It's going to be a 4D plot. So what we do is we plot the magnitude as a function of s and the phase as a function of s, or sometimes we can plot the real part and the imaginary part of f of s. Now this is not complete because this here requires us to say that the region of convergence is for sigma greater than -3. So if you come over here, you say that this is the -3. The region of convergence is this portion on the graph, which makes the function, if you're going to plot the function on the region of convergence, right, you're going to plot it from -3 onward. So this is the function that we will have it. Because at -3, it's going to give me a spike here, right, -3 and 0. I plotted it a little bit higher than -3, so you can see the way the function is. So what I did over here, I said that I'm going to plot it for the region of convergence, which is you take s equals -3, so that's over here, and then you're going to go higher than that for sigma greater than that. So this is the region of convergence for f of s, and that's the phase for the same region of convergence. You can also plot it as a real part and imaginary part. So any complex function, when you plot it as magnitude and phase, or real part and imaginary part. Again, it's a 4D graph, so you have to break it into 2 3D graphs. So to plot f of s, we get the real part and the imaginary part, or the magnitude and the phase. So the question that I have to ask is Laplace transform a one-to-one transformation? So basically what we said, that if we have f of t and I'm going to convert it to f of s, is it always that f of s will be converted back to f of t? Is it a one-to-one transformation? And the answer is no. There's conditions that has to be applied to guarantee that it is a one-to-one transformation. So for example, we know that if you have f of t will be a times e to the minus at u of t. This is a causal signal. Its transformation gonna be a over s plus a as long as sigma is greater than -a. We know that. So now let's do this example. Let's look at another example using the Laplace transform. We're gonna say that let f of t be minus a times e to the minus at times u to the -t. This here says that u of t is inverted in the time domain. That means that this function is non-zero for all values of -t, and it is 0 for all values of positive t. So it is called anti-causal. Anti-causal means that it is 0 for all t greater than 0 and non-zero for t less than 0. To do the transformation, it's basically using the double-sided transform. It's going to go from -infinity to 0, right? Because this is when this function is non-zero, is for -t. So the integral is going to go from -infinity to 0 of minus a times e to the minus at times e to the minus st dt. That's just by the definition of the Laplace transform. It is 0 for positive t, so the integral is going to be 0 for positive t, but it is non-zero for -t. So I'm going to pull the -a outside, and I'm going to integrate from -infinity to 0. And those two functions are exponential, so I'm going to add the exponents. That's what I have here. So I'm going to get the entire derivative of that. So I'm going to get minus a over, and then I'm going to divide the exponent of that, which is minus s plus a times e to the minus sat, and then I'm going to integrate from -infinity to infinity. Clearly that this minus on the top will cancel the minus at the bottom, and that's going to be positive. And then I'm going to basically evaluate at 0 minus the evaluation at -infinity. So clearly that this term here is going to go to 1, and we have to deal with this term. So now when you multiply this minus by this, becomes positive infinity, and then this becomes the first term is the same, a over s plus a, and then I will have times 1 minus, and the minus is cancelled because you multiply this negative times the minus infinity, becomes plus infinity, and I replaced s with sigma plus j omega. So now what I'm going to do is I'm going to break the real part terms together and the imaginary terms together, and I'm going to break this addition of the exponents to become two functions multiplied. So, and then this basically will equal to the a over s plus a going to be the same. I will have the 1, and over here I end up grouping the real parts together, so I will have e to the sigma plus a times infinity multiplied by e to the j omega times infinity. The magnitude of this is always 1. The phase will change as you go to infinity. It's going to always be between 0 to 2 pi. However, for this one here, I'm interested in this term, the sigma plus a. As long as this is negative value, which is less than 0, this will always go to, it's going to be e to the minus infinity. And e to the minus infinity will always go to 0. So this will go to 0 as long as sigma plus a is less than 0. So then I can say that, because if this is the case, will be 0, then the transformation will be a over s plus a as long as sigma is less than minus a. When sigma plus a is less than 0, that means sigma is less than minus a. So here is the catch. This signal has this transformation, but the region of convergence is that. This signal have this transformation, but the region of convergence is that. So then what we do, we say that f of t will equal to minus a times e to the minus at u of minus t. Its transform is f of s will be a over s plus a. It's the same signal, it's the same function. The only difference is the region of convergence. They're going to be different. So what that means here is that those two functions are the same, but the region of convergence are different, and that's what distinguishes them. Then we can say that the function, it is one-to-one mapping if the signal is causal, which is a practical example. So for causal signals, we can assume that it is one-to-one mapping. Or for anti-causal signals, we can assume they are one-to-one mapping. And that's something that we need to pay attention to. Now, when you calculate the inverse, those region of convergences are important. And that has to deal with how you're going to calculate the contour integral, right, when you calculate the inverse. So let's elaborate a little bit on the two functions to see the difference. So in the first function that we did, right, if you said the first example that we solved, we know that the function is exponentially decaying function. And we said that this is basically the function that you have, but more important is the region of convergence. The region of convergence is for sigma greater than -3. So for the second example, you get the same Laplace transform. The region of convergence is different. But if you plot the function itself, it's kind of interesting. For positive t, it's 0. For negative t, it's going to start in this example at -5, but will blow up to negative infinity as t goes to negative infinity, right? So it's a blowing up function, right? It's actually coming in from negative infinity all the way to -5. And then it goes to 0 for t greater than 0, right? This function and this function are different, but they will have the same Laplace transform. They do have different regions of convergences, and that's important. Because when you have the functions like this, but the regions of convergences are different, the first one, it says that sigma is greater than -3. The second one, it says that sigma is less than the -3. The region of convergence is extremely important when you calculate the contour integral. When you use the partial fraction expansion, there is nothing you can do, so you get confused. But when you calculate the contour integral, the region of convergence becomes very important, because here, as j omega will go from minus infinity to plus infinity, the direction of the contour will go counterclockwise, and when you calculate the contour counterclockwise, this basically means that it is causal signal, the time moving forward. However, here, when you go from minus infinity, when j omega goes from minus infinity and come back to the plus infinity, here you are going clockwise, and when you calculate the residue integral on the clockwise, this will lead to anti-causal signal, right? Time will be going in the inverted direction. That's something that you have to pay attention to, and to understand that you have to know complex variables. So the answer basically, no, it is not a one-to-one mapping unless you wanted to stress the region of convergence, and it is not a one-to-one mapping if you're going to do partial fraction expansion, unless you wanted to stress the region of convergence, and that's extremely important. So the question now becomes, why Laplace transform is important? Why do we use it? And the trivial answer is that Laplace transform is used to solve differential equations with constant coefficients. It's the general solution to differential equations with constant coefficients. Why differential equations with constant coefficients are important to us? Because linear and time invariant systems are modeled with differential equations with constant coefficients. And then you can use Laplace transform to solve for that system. And that's where we get into the concept of impulse response, transfer function, convolution becomes multiplication, and all that, which will be a topic that will be discussed in another video. Basically, to be continued. I hope you like this video, and good luck to you.